Okay, so now we're going to do the second example in our part 2 of solving differential equations using series of functions. So here's our example. Find an approximation to y double prime plus y equals 0. So the second derivative plus the original function add together to get 0, where the initial condition is at 0, the function is 1. All right, so we'll start with a regular series for y, comma. We find y double prime. If you scroll back up with your notes, you'll find out, what y is. Take the second derivative, the derivative, that kind of stuff. You find it's a2 plus a3x plus a4 over 2x squared. It looks just like the original derivative or original function, except all the indices have been moved up by 2. All right. So now combining like terms, if I add y double prime to y, the constant from y is a naught. The constant from here is a2. So a naught plus a2 plus a1 plus a3 times x plus a2 over 2 plus a4 over 2 x squared and so forth. So notice a 0 and a 2 and a 2 and a 4. Here's a 1 and a 3 and a 3 and a 5. So there is a pattern here that in each of these little parenthetical things, if n is the power outside the x, then down here I have an an over n factorial plus a sub n plus 2 n factorial. So this is a squared here. So here's a 2 and a 4 over 2 factorial. This is cubed. So here's a 3 and a 5 over 3 factorial. And that's a 3 factorial there too. So that's the pattern. So we could write out as many terms as we want to without thinking too hard. All right, so now again, with our initial condition being 1, y of 0 equals 1, that means a naught is 1. And then we can start realizing, hey, that pattern we had before lets us find out some stuff very, very quickly. If a naught is 1 and a naught plus a2 is 0, because the whole differential equation is equal to 0, so each of these parenthetical things must be 0, then a2 must be negative 1. But jump 2 places ahead, now I have an a2 plus a4, that's going to add up to 0 too. It means a4 is positive 1. And if you realize, oh, I'm going to go from a 1 to a negative 1 to a 1 to a negative 1, we can extrapolate the even ends are all going to switch between plus and minus 1. If you think about it, this is a little bit harder. The multiples of 4 are going to be positive 1s, and then the other evens, the other half of the evens, will be negative 1s. Okay, that's a formula we can come up with. But then I realized I haven't answered anything about the odds, and I've used up my initial condition already. All I can do is say, if I think about the same logic as before, all I know is that a3 will be the opposite sign of a1. So a3 is negative a1. And I come over here and realize that a5 is negative a3. So actually a5 is a1. So I have this pattern. I have 1 plus a1x minus a half x squared plus this a3 is actually negative a1. And this a5 is actually a1 as well. And then, frankly, I think this little minus sign right here is a typo. Sorry about that, folks. That should be a plus right there. Just goofed it up. I was thinking in advance, eventually it's actually going to be a negative number. Actually, sorry, I should stop talking. But then if I pull out all those even terms, then I have a 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. You recognize that is the formula, the series expansion for cosine of x. And then this is where I actually drill into it. Now here I have my coefficient right. There's the plus that should be right there. If I think about this series expansion, when I replace a1, or a1 stays the same, but a3 is replaced with negative a1 and a5 is replaced with positive a1, I can recognize that if I factor an a1 out, then I actually have the series expansion for sine. We'll get to that in a second. So what I have is a second order differential equation, and I have one initial condition. So if we go back to DE's class, you recognize that if you have a second order differential equation, I need 2 initial conditions to nail down the solution. Otherwise, I have infinite solutions like I do in this case, all depending on what I choose for A1. So I need one more initial condition. And so here are just 2 options. Out of infinite options, here are 2 that are interesting. One is, what if I set the initial condition of y prime to be 0? And that means A1 is 0. And that means all of this stuff is 0. My final answer is that cosine x is the solution. And if you think about it, the original equation is a function that when added to its second derivative is 0, or a function that's equal to the negative of its second derivative. And cosine's derivative is sine, or negative sine, whose derivative is negative cosine. Sure enough, they're opposite signs. All right. Another initial condition that would be a common one to try would be that y prime of 0 is equal to 1. And then a1 is 1, and then all those coefficients from up here just alternate between 1 and negative 1. And that is sine x. I get the solution cosine x plus sine x. And then you can take its first and second derivatives and verify that, yes, this does satisfy that initial condition. And again, I'll take this one here and I can plug that into Mathematica. And so I know that the solution is cosine x plus sine x. But I could have stopped with what I could see here on the screen. I could have stopped with, this up to the 4th degree here, and frankly, I could have just stopped right here with the 3rd degree. You'll see in the homework that I'm going to have you stop at quartics. So I'll stop at the quartic and throw in this x minus x cubed over 3 factorial term. And if I graph those together, you can see that the original function in blue does closely match the approximation, this golden rod, in between -2 and 2 roughly, or between -1 and 1 really well. It does a good job of approximating the function. All right, the next video is going to go through the homework set and give you expectations for that.